Okay, here with a Tuesday edition of AP Calculus. How's everybody doing? Uh, I've been going through it here, feeling fine, but I walk out to my car yesterday. I haven't driven it in like a week or two, and a nice crack in the windshield. It's like, oh, good. Get to go get that replaced. Just sitting in the driveway. Okay, enough of me venting because I don't have anyone to vent to, except the YouTube community, obviously, now. Let's get going through here. So we're looking at 2014, and I gave us 3 through 6 to work on. So this first one is one of these ones where they give you a graph, but then in the question they define this as some g function with an integral. So really the way to think of this graph is like g prime. And here the first thing they want us to find g of 3. So really that's just putting 3 into the integral, which means they want the area under the curve from -3 to 3. So if we're looking at this picture, that means -3 is here. We need that area, and then notice 3 brings us there. So the large striped triangle has a base of 1, 2, 3, 4, 5, and a height of 4. So that's going to have an area of 10. And then this little one, it's a 1 by 2, it's looking like there. So that's going to have an area of 1, and we need to subtract those because the smaller darkened in one is underneath the x-axis. So we have to subtract that. And the other one was above it, so that was positive. So there's our area there for A. And that's a good old 1-pointer there. On what open intervals contained for the whole graph is g both increasing and concave down. So we're increasing when g prime is greater than 0, which is just saying that f is greater than 0, which we can see here is from -5 to -3. It doesn't include -3 because that's 0 there, and then -3 to 2. So that's where it's increasing, but we also want to know where it's concave down. And concave down is going to be when the derivative is less than 0, or where this graph is physically decreasing. So -5 to -3, it's decreasing. And it's also decreasing from 0 to 2. And since both of those kind of overlap here, this would be our answer, where it's doing both of them. And the point breakdown here is they give 1 point for correct answer and then 1 point for reasoning. So kind of writing this all out, saying where it's positive or where it's negative. So 2 points overall. Next one they're looking for here, they give us some weird h function, and then it wants to find h prime of 3. What we need to do here is they want the derivative at 3, so that means we need to take a derivative. Left side, nice and easy. Right side is where a little bit of a challenge here. Looks like a quotient rule is going to need to be had. So fig minus gif all over g squared, so 25x squared. Okay. We can't really simplify our lives too much here. The only nice thing that we can do is there's a 5 in everything, so that can be factored out. But that's about it. But they wanted this at what value? 3. So h prime at 3 equals g prime at 3 times 3 minus g of 3 all over 5 times 9. Okay, g prime of 3. That is basically, remember, if this is g prime, what is the value at 3? And the value at 3 here is -2, we'd already said. So -2 times 3. G of 3 we'd found up here as 9, and this is all over 45. So we have -6 minus 9 over 45. That is -15 over 45, which would be incorrect based off of the AP exam because they want it simplified. So you do have to write it as -1/3. What's really nice here is they give you 2 points just for this correct derivative. Without simplifying, it doesn't matter. Just getting here using the correct quotient rule, and then 1 point for getting to that number answer. And then the last one we're looking at here. We have this p function, and it says find the slope of the tangent line of the graph of p when x is -1. So if they want the slope of the tangent line, that means we are going to have to take a derivative. And this is going to be a chain rule. Derivative of the outside function is just f prime. And then the inside is going to get us 2x minus 1. And now they wanted this specifically at the -1 value. So this is 1 plus 1 times -3. So we need f prime of 2 times -3. F prime of 2. So this is f. If we want f prime at 2, that is not the value here. That is what is the actual slope of this line. And if you're looking, it's going down to over 1. So it is a -2 slope. So 6 is what we're getting at here. Point breakdown, yet again, really nice. 2 points for that correct derivative. 1 point for actually doing the math afterwards. Pretty common trend. Okay. Hopefully these are getting a little better, these styles, because they're on pretty much every single one to see like the graph of the derivative is given, and then you find out some info from it. Another pretty common one here is where they give you kind of this chart, and I'm typically thinking that this is going to be a Riemann sum question. And I guess this is the average speed of some train A. It says find the average acceleration of the train over the interval from 2 to 8. So we find the average of anything is subtract it, divide by the difference. So we're looking for VA of 8 minus the velocity of A at 2 all over 8 minus 2. So -120 minus 100 over 6. And this is going to be -220 over 6, which is -110 over 3. Technically, it's meters per minute squared. However, I don't think they ask for units, so it doesn't matter. Just that number is what you want. Yet again, it needs to be simplified. This -220 over 6 is not going to get you full credit. This will. Just a 1-pointer here. Boom. Okay. Do the data in the table support the conclusion that train A's velocity is -100 meters per minute at some time between 5 and 8? So if we're looking between 5 and 8, and we go from 40 to -120, we want to know, will it ever be -100? I think common sense makes you say yes. It does have to actually hit there, right? Because think we're going forward to all of a sudden it's going backwards and it's accelerating backwards at a faster rate. But how do we kind of defend all this? So there's one key word in this question that's going to be big for us, and it's that it's differentiable. remember, if something is differentiable, that implies that it's continuous. And if it's continuous, that means there's no jumps or kind of blips in the graph, which means it has to hit every value, in fact, between 40 and negative 120 in this time frame. And what that is called is going to be the intermediate value theorem. So you need to go through and state, since 120 is less than 100 is less than 40, so by the intermediate value theorem, yes, you can just abbreviate it. Train A must hit negative 100 meters per minute. And this one is worth 2 points, once for using some IVT and once for denoting that the negative 100 is between those two values. Okay, at time equals 2, its position is 300 meters east of origin station. Don't they think they're being so cute, origin station? Ugh. And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time equals 12. And use a trapezoidal sum with 3 subintervals on the table to find the position. Okay. So, remembering how we get position from velocity. So our position is typically whatever your starting point is, which here it was, what they say, 300, 200, 300. And then we're going to add on that integral from 2 to 12 seconds of the velocity of A, and make sure you put with that respect to t. Right, so we start at 300, so that 300 is just there, and then the integral is going to get us to where we're actually at in the position over that time. Now they want 3 subintervals of trapezoidal sum. If you remember, the area of a trapezoid is 1/2 base 1 plus base 2 times height. And Lucian asked about this specifically, and I think I can draw a quick little picture here that may help us see this a little bit better. So at 2, it's up at 100. At 5, it's at 40. 8, it's negative. And then 12, it's also negative. And they want to do trapezoidal sums. So we can make a trapezoid here. Is one trapezoid we're finding the area of, and then kind of the next trapezoid, and then the next trapezoid. And I might have botched that second one. I think the second one's looking more like this. Anyway, it's going from each piece, and we can look at all those different trapezoids that are made off of them. So how we actually connect this in the question is we have our 300, and let's go through 1/2 base 1 and base 2 of the first ones here. So that's 100 and the 40. And then we need to know what that height is. Height here is the difference between them. So between 2 and 5, these are 3 apart. Next one, 1/2. The 2 that we're using here are 40 and negative 120. And the height, or the difference between these here, is also 3. And then for the last one, we have 1/2. Our bases here are negative 120, negative 150, and the difference here is not 3. It's 4. Goes up one little bit. At this point, it's just a whole bunch of arithmetic to add this all together. On the AP, you will be given like a 4-function calculator you can use it's legal. So that comes to negative 150, which means it's actually on the other side of the origin, the station. Does it want you to even go into that? I don't think it matters. Okay, so point breakdown. 1 point for this initial expression, 1 point for writing this trapezoidal sum out, and then 1 point for doing all the math to get that negative 150 there. Okay, and last bit. Second train is traveling north, and we have this equation. Find the rate in meters per minute at which the distance between these trains is changing, A to B. This one's nice if you're looking at a picture of it. Train A here, train B here, and we know this initial distance is 300, and it's moving out at a rate here, they said, of 300 meters. Oh wait, no, at 2 seconds, sorry, 100 is given in the question itself. So at that exact moment, at time t equals 2, it's moving out at 100. B is 400 north, and hopefully you're seeing this. You see 300, the 400, like, oh, we've done a bunch of these. I know the distance here is 500, a little Pythagorean triple there. But we need to know what the distance is of, what the speed of this train is, train B. So let's put in 2 here. Negative 5 times 4 plus 60 times 2 plus 25. Negative 20 plus 120 plus 25 gets us 125. And that's a positive one. It's moving up at a rate of 125. And we want to know what this distance is changing at. So you do need to write out your expression, x squared plus y squared equals z squared. We can take the derivative with respect to time here. Didn't we miss implicit differentiation? So much. They all have the 2 here, so we can kind of factor those out, at which point we can just plug in the values we know. So we have 300 and 100 here. For the y, we have 400 and 125. And for the z, we had 500 dz dt. So we have to add those up, divide by the 500, and doing that all out is going to get us 160 meters per minute. Okay, through 2 of them, halfway there. Okay, so we have a twice differentiable function here, f and g, for all real numbers x, and they give you a handful of different things specifically. So this is kind of an off question for the Regents, or not the Regents, the AP. They will throw wildcard questions in there, about 1 every test. I don't really know how it's going to work this year with just 2 questions being asked. But this chart one was one where it's like, huh, this is a little different. Let's find the x-coordinate of the relative minimum of f on this interval. So if I want to find out where the minimum is, that means I want to know where it goes from decreasing to increasing, which means that I want to look at the derivative. So looking at the derivative, they're negative here. That means it's going down, decreasing. That's a good start. It's still decreasing. Now it's increasing. So where does it switch from decreasing to increasing? Right here. And it's not at 0. It's at the x value 1. So hopefully that makes sense. So the slope is 0 here at 1. So the answer, find the x-coordinate and justify your answer. So x equals 1. It goes from negative to positive, to use their words. If you use decreasing, increasing, that'll work as well. Next one. Explain why there must be a value c between -1 and 1 such that f double prime of c equals 0. So between -1 and 1, that's here. And we have the first derivative, and we know that both of these values are 0. So we know f prime of -1 equals 0, and f prime of 1 equals 0. But we don't know anything about the values in between. But remember way back, what unit was this? If we have a value that's -1 and 1, and you're connecting these because we know it's continuous, no matter how you connect it, whether you kind of put a valley, if you made a hill, or whatever it was, that at some point in between there, it's going to turn, even if you made a straight line. So this is actually going to be true by the mean value theorem. Usually we use the mean value theorem on just the first derivative to know that the slopes are going to be there. However, you can use it for the second derivative if you're looking at the first derivative. But we need a little bit more than all of that in here. We do need to state that the mean value theorem says there exists some number f prime of c where this is going to work. But since we're working with the second derivative, we just add a derivative mark into all of these. Same thing is going to hold and be true there. And so if we were looking at these values, f prime of 1 minus f prime of -1, it's 1 minus -1. So that should work. But remember where I used to like ding us quite a bit for mean value theorem. What do you need to be true about a function for us to be able to use the mean value theorem? You need that the function is continuous. Yet again, that keyword differentiable is going to help us out. So since it's differentiable, it's continuous, so that we can use all of this. And kind of that all needs to just be put together to get us there. So point breakdown, 1 point here for this question, 1 point for showing there's 0, and 1 point for using the mean value theorem with a nice explanation, which is where I think you need that it's continuous. Okay, they give us some weird function h, and they ask us about the derivative. So I really like these questions because it doesn't actually involve you having to do any other parts in it correctly. You could just jump here. Since we have h of x is ln of f of x, derivative here means we're going to have to do some chain rule action. Derivative of ln, 1 over f of x, but we still need the derivative of the inside, so we still need f prime of x. Since they wanted this specifically at, what number? 3? 1 over f of 3 times f prime of 3. So now we got to go up to the table. F of 3 is 7, so we have 1/7, and the derivative there is 1/2. So looks like 1/14 is going to be our answer. Yet again, AP is huge. I'm just giving you 2 points for the correct derivative, 1 point for the numerical answer. And then last bit wants us to evaluate this big old ugly thing. From -2 to 3, f prime of g of x of g prime of x with respect to x. Maybe you're looking at that and saying, I have no idea what that antiderivative is. They don't really give us any functions up here. What are we supposed to be doing? And maybe you take a closer look at this and say, this looks a little familiar. Looks kind of like what we were doing up here as well. This is going to be kind of the chain rule, but in reverse. So if we take the antiderivative here, we should just be left with f of g of x. If you're saying, what? Try taking the derivative of this thing, right? You take the derivative of the outside, inside stays the same, the derivative of the inside. So this does work out nicely. Now you just have to plug in the values and see what we're getting. F of g of 3 minus f of g of -2. So we need to find what g of 3 is. It's the only time we use this g in here. So this is f of 1, right? Because g of 3 became 1. g of negative 2. G of negative 2 is negative 1, so we have f of negative 1. F of 1, 2, minus 8, negative 6. They gave us 2 points for just getting that that's the correct antiderivative, and yet again, 1 more point for correct evaluation. Ooh. 25 minutes in, 3 questions down, 1 to go. Keep in mind, for your first question, you're going to have this amount of time to do the whole thing. And I'm guessing it's probably like one of these questions, but maybe one more part. So maybe it's like a 5-parter. Okay, and the differential equations. These are really my favorite ones on here because we're just doing the same thing time and time again with these questions. The only little difference here is they give us a slope field to actually kind of do out. And it says a portion is marked below, sketch the solution curve. So this would be the slope field for this 3 minus y cosine x. But they tell us we have the point 0, 1. So you pick your point 0, 1 there, mark that. And then it's just kind of sketching what's going on there. So it goes up, kind of flat lines there. It's going down over. And then we need to know what's happening over here. So you just kind of follow along with the lines. And it's going to look something like that. They're typically pretty lenient with the sketches and stuff like that. And honestly, if I had to guess, they're not going to give us a question like this since you're not going to be printing it out. You're just writing your answers down. So I wouldn't assume that this would be on there. But in case, there it is. Write an equation for the line tangent to the solution curve in part A at the point 0, 1. So we need the equation of a tangent line. So we need a point and a slope. We have the point. We need the slope. Thankfully, they gave us a slope equation anyway. So we need to evaluate this at 0, 1. So that's 3 minus 1. That's a tough one. 2. Cosine of 0. This is where I'd make Ramelan sweat, and he'd sit there and hem and haw, and then say an answer that's right, change his answer to something that's wrong, and then we'd all move on with our lives. So cosine of 0 is 1. And we have 2 here as a slope. We got the point and the slope, so the tangent line equation that we can write down is y minus 1 equals 2 times x minus 0. If we wanted to write this kind of nicer, that's just 2x plus 1. And it said use this equation to approximate at this point. So we have 2 times 0.2 plus 1 equals 1.4. Great. By the way, point breakdown, 1 point for this nice little 1 point for the tangent line equation, and 1 point for getting that number. Now find the particular solution to this differential equation and use that initial condition. Okay, so we're taking this equation. We have to separate variables. That's always the first move here. And yet again, we cannot just like add or subtract them. You have to do division and multiplication to move them around. So the x is coming over. It becomes 1 minus 3y in the denominator, 1 over 3 minus y. Let me speak correctly. In the denominator here. And we've properly separated variables. Let's do some integration. Okay, right side is the easy side, so dibs. Sine of x plus c is what we're getting over here. On the left side, this is going to look like a natural log or an ln, but keep in mind since it's a negative variable underneath there, if you did the u substitution and wrote this all out, it will pop out a negative ln. So it is a negative ln of 3 minus y. is what we should be getting here. Okay, once we're here, let's use that initial condition to find out what the c is. So we have negative ln of 3 minus 1 equals sine of 0. Sine of 0, yet again, let's ask Ramalan. He actually gets this one right, surprising even himself here. And we get that c is just going to equal negative ln of 2. Going back to the equation, negative ln 3 minus y equals sine of x minus ln of 2. And at this point, they wanted y equals form, so we just got to kind of rework this. It's slow and annoying, but we'll get there. Negate everything first. So ln of 2 minus sine of x. We can e everything here. Kind of knowing a little bit about what's going on with e's and natural logs, this can actually be rewritten really nicely as 2e to the negative sine of x. So I think I talked about this in one of the first videos I did on differential equations. With adding or subtracting in here, it's like you're multiplying the different ones, so it's really like e ln of 2 times e to the negative sine x. So the e ln of 2 is just the 2. We're still multiplying the e to the negative sine of x, so that's okay. Subtract the 3, negate everything. That's all just going to leave us with 3 minus 2e to the negative sine of x. And there we go. Oof, pumped through them in 32 minutes. Not too bad. Hopefully you're taking the time to actually go through these and look at them and try them on your own beforehand and not just hear me going through them, because that's not super useful to just have me talk over them. I mean, I do know that you guys are all probably missing my voice on the daily calc classes, but oh well, we're going to have to make do. Okay, let's look at what I want next. Let's look at 2015. Do I like all of these? I like 3, I like 4, I like 5, and I like 6. So let's look at 3 through 6 here. Reminder that our exam is in about 3 weeks or so. So we still got a little bit of time, but we still got to be pushing hard here. Okay. Stay safe, guys. I will try to get another video up and going this week. Please comment below. I want to see that you're actually looking at these. I think I've had like 6 people comment. Comment, say something so I know you're alive and just pretending to do math. Okay, bye guys.